let's have a look at this next section in this handout on equations of motion, and consider this, what happens when we take this further and talk about forces acting on bodies. So for linear motion, we've got the familiar formula, force is mass times acceleration. So this formula should be one that you're very familiar with. We talked about how bodies accelerate and the relationship between the acceleration, the final velocity, initial velocity, and so on. Okay? What we need to do now, just like for angular motion, there's equivalent equations of motion for angular velocity that we used. There is another formula that we're going to start using now, which gives us the applied torque to something to try and make it turn. So the torque is to do with the size of the force and how far away it is from the moment of, or the center of rotation. But also we can write down that the torque equals the moment of inertia, which is equivalent of mass in linear motion and angular velocity. So we've got this new formula now that relates to torque, the moment of inertia, and the angular acceleration. The formula, torque equals I alpha, is derived in the notes that follow by considering unit mass and what happens to that, and then considering what happens as this unit mass moves away from the radius, the center of curvature, and then sort of taking that all into account. We're not particularly going to look at that, but it's in the notes, so if you want to look at it. And they talk about in the notes the idea of what happens to this delta M. Delta M. This symbol here, delta. Greek alphabet, delta. We also have the capital delta that looks like this. And they tend to mean changing, generally a small change in. So for a small amount of mass, or a small change in mass, delta M. By considering that, you can then derive the formula torque equals I alpha. So that's one thing. In problems, you're often given, okay, the moment of inertia or the way to means to find it, and the torque, find the angular acceleration, and so on. So really, when it comes down to it, you just need to be able to use this formula. Often, because we're talking about some object rotating, we consider unit mass, say here, rotating a distance away from the center, called the radius of gyration. So instead of considering the radius of the whole thing, we define this thing called radius of gyration, which is then allows us with that to come up for the moment of inertia. If I want to find the moment of inertia of a body, I just multiply the mass by this radius of gyration squared. And there are a couple of formulae that are worth making a note of. Two rotations that we consider. One is a solid flywheel rotating. The other is some rotating body with a rim and no mass in the middle. So there are two considerations, 1, 2, and there's two formula. K, the radius of gyration for a solid flywheel, equals the radius over the square root of 2, and that can be derived. And for a flywheel, the radius is the mean radius. K equals the mean radius. So that could mean to the center of this thing. So the same sort of considerations that we were taking into account for earlier problems for the bending equation, stuff like that. So we've got this R mean. So in problems that we're going to look at examples of in a minute, we need to be able to calculate what this moment of inertia is. And the moment of inertia in rotation is equivalent of mass in linear. Once we've got the moment of inertia, we can then go back to this equation and find the torque. And the relationship between the torque, the moment of inertia, and the alpha, the angular acceleration, is exactly the same as the force, the mass, and linear acceleration in straight linear motion problems. Okay. Let's have a look at one or two examples, and then I think that'll become clearer. So the first example to look at, this one, is in the book. Find the moment of inertia of a component given that its mass is 15 kilograms and the radius of gyration is 200 millimeters. So if I just pause this for a sec, have a go, and then we'll look at it together. So as with all problems like this, which is the formula you're going to use in this case? Is it in the right form? Are the units consistent? So formula, I equals mk squared. One of the ones on the previous sheet, where m is the mass and k is the radius of gyration. So we want to find the moment of inertia, so it's in the right form. I equals, all we need now is the mass and the radius of gyration. We're given the mass and we're given the radius of gyration, so what's the only other thing to consider? Units. So m equals 15 kilograms and k equals 200 millimeters. And what do I do about that? Turn it into meters, yeah. 0.2 meters. So those are the values you're going to put in, 15 and 0.2. Kilograms go with meters. So we plug that in and we get the value for the moment of inertia. Which is not quite, I don't think. 0.6, yeah. Ah, right, okay. So be careful then, because it didn't work going the other way, did it? Because yeah, because of the square term. Unit for moment of inertia, would you say? Units of mass? Units of radius of gyration? Kilogram meters squared. So the units come directly from the formula. So that's the moment of inertia, which is the equivalent of mass. Now, if I was given the torque acting on this flywheel, I could find out what the angular acceleration was. Or if I was given the angular acceleration or the means to find it out, I could work out the torque on the flywheel. And we're going to look at some examples like that, okay? So if we've got problems to do with flywheels, we're not interested in the mass when we come to problems, we're interested in the moment of inertia, so we need to calculate what that is. And that has the same sort of meaning as mass does in linear motion problems. Okay. Let's look at the next one. A flywheel has a mass of 100 kilograms and its speed is increased from 600 to 700 RPM in 12 seconds. Assuming uniform acceleration, estimate the required torque for both types of flywheels shown below. So let's have a look at these two flywheels. Let's talk about one solid one with a diameter of 60 millimeters and so this is a solid flywheel rotating, and then we'll look at one where all the mass is concentrated in the rim. Again, the diameter is 60 millimeters. And as it's all concentrated in the rim, we assume that this distance here is the mean radius. So the first thing to do is to find out what the moment of inertia is for each of those flywheels. So if I could ask you just to do that. Find the moment of inertia, which we did for the last question. And then once we've got the moment of inertia, we can find the torque. But we'll look at that together in a moment. So let's look at the first problem for the solid flywheel first, and go through the same sort of thing we talked about before when solving problems like this. What you asked to do, you're asked to find the required torque for the solid flywheel. So my start point is the formula for torque, which is by alpha. Okay? Now, if I'm told I can just plug it in. If I'm told alpha, I can just plug it in, but I'm not. So what I now need is to ask myself, okay, how do I find I? What's the formula for I? mk squared. So do I know k? So do I know n? Yeah. Do I know k? I can find it, can't I? For the solid flywheel, k equals the radius over the square root of 2. And I know the radius, so I can find k. I can plug that into this formula here to find I. Once I've got I can plug that into there. So that's my approach to that bit. Alpha now is a problem. So what I need to do now is to go back to what we were doing before and think of a formula that will allow me to find alpha in terms of what I want to know. So let's have a look. I'm told its speed increases from 600 to 700 in 12 seconds. So for this one, I know that omega 2, remember we've got omega 1 and omega 2, and the time. So omega 2, the final angular velocity is 700 RPM, and that's 600 RPM. But that's actually not angular velocity, that's the frequency, isn't it? So the frequency. And the time was 12 seconds, I think, wasn't it? Is that right? Yeah. What's the relationship between angular velocity and frequency? And what's the formula I'm going to use to find alpha? So alpha equals omega 2 minus omega 1 over t. So to be able to use this formula, I need to know the time. I know the time, that's 12 seconds, but I don't know omega 1 and omega 2. What's the formula that relates omega 1 and omega 2 to frequency? Very familiar formula, I hope, that relates frequency and angular velocity. 2 pi f. So the frequency needs to be in hertz, which is revolutions per second. At the moment it's in revolutions per minute. So I need to convert this frequency to revolutions per second, and then that can go in there to find omega. Once I've got omega 2 and omega 1, and I can subtract one from the other, divide that by t to get alpha, and then that goes in here. So I don't know how you would prefer to set these things out, but this is a sort of process that goes on in your head or on paper. This is the formula. So how can I find out what I is? This is the root, and so then go back through the root to get it. How do I find alpha? This is the formula. That's how I find omega, so now I can do it. Okay? So do you want to go ahead and see if you can find the torque on the solid flywheel and then the torque on the rimmed flywheel? Let's look at the solution quickly. What I've done is actually left it in terms of pi, which is not uncommon actually with rotations, because pi left at the end can often either cancel out or you can leave your answer in terms of pi. So although you might think, well, let's just do it on a calculator, sometimes leaving it in terms of pi is useful. So let's look at it just as an exercise anyway. Warren. So that's throwing you right out at the start, as it was. Right, okay. So divide by 60 will give you number of rotations per second. So, right, so let's go through this then. So first of all, let's find alpha. So alpha is given by this, look, so we need omega 2 and omega 1. So omega 2 is 2 pi times the frequency, which is 700 divided by 60, which turns out to be 70 pi over 3. Radians per second. Omega 1, 2 pi times 600 over 60, which turns out to be 20 pi radians per second. So alpha then, omega 2 minus the omega 1 over 12 seconds. Writing them both in terms of thirds, 20 is 60 over 3. 70 minus 60 gives you 10 pi over 3. 3 times 12 is 36. So I get alpha to be 10 pi over 36 radians per second squared. If you want to know what that is on the calculator, that's, if you work out that, that should be the answer you get anyway in radians per second squared, 10 pi over 36. So in green, we've got the approximate answers that you might get on the calculator, but of course, leaving it in terms of pi, this is an exact answer. Whoops. Oh, what have I done? I don't know. This is an exact answer, okay? 10 pi over 36, or 5 pi over 18. Yeah. Yeah. Oh, perfectly acceptable. Yeah, I'm not saying you must do it this way. I'm just saying, yeah, often when you're doing a lot of work with rotation, you will find that leaving the answer in terms of pi is the best way to go. And so that's what I've done here. But if you want, you're just after an actual value for it, 0.875, whatever it was, appears to have disappeared, then that would do in most situations, okay? Okay, so now we've got a value for alpha. We can now plug that into the formula for the torque here. But we also need the moment of inertia. So the second question was, what's the moment of inertia? Well, if we use K, because it's a solid flywheel, K is 0.6 over root 2, then I turns out to be the mass, which is 100 kilograms times 0.6 over root 2 squared. So that means you actually end up with 0.18 kilograms meter squared. Is that correct? Ah, yes, I have gone wrong. 0.6 is diameter, so it should be 0.3. Well spotted. So now I need to change this. So now that gives us I equal to 4.5, so therefore the torque will turn out to be 4.5 times that, which gives us a different answer altogether. So it's 4.5 times 10 pi over 36. So that's equal to 45 pi over 36. Is there a number that goes into 45 and 36? No, so that would have to be the final answer, okay? Which you could then work out on the calculator. And won't it? Right. Possible. So we get an answer of 5 over 4 pi, which is 3.93 newton meters. Now try this. Okay, try it for the other one. So instead of k being r over root 2, because it's a solid flywheel, use k is just the value for r. Okay, and see what you now get for the torque, and you should get something like this.